Welcome to today's Explainer. We're doing something a little different today. We're going to take the pretty grim reality of water pollution and turn it into an empowering engineering masterclass. I'm literally thrilled to guide you through this because, hey, we aren't just staring at a massive global problem today. We are systematically designing the solution.
All right, let's dive right in. Picture a simple, clear glass of water in your mind. Now, imagine that glass represents literally every single drop of water on planet Earth. Well, the stark reality is that less than 2.5% of all that water is actually fresh water. And get this, most of that tiny percentage, it's locked away in ice caps and glaciers. So the accessible water in our rivers, lakes, and aquifers, that is all we really have to sustain life, agriculture, the whole shebang. And the hard truth? We are actively poisoning the incredibly small amount we actually have access to.
And, this perfectly illustrates why we're not just dealing with a purely ecological issue here. This is a catastrophic human issue. According to the World Health Organization, an absolutely staggering 80% of all infectious illnesses spread through contact with contaminated water. That little fact takes this from being, just an environmental concern straight into a massive, immediate public health crisis.
To tackle a crisis of this scale, we need a rigorous structure. So here's our syllabus for today's session. First, the freshwater crisis. Then, 4 types of pollution. Third, sources of contamination. Fourth, the engineering solutions. And finally, a call to action. Okay, let's get into it.
Section 1. The freshwater crisis.
Now, what exactly do we mean when we say water is polluted? Well, water pollution happens when the physical, chemical, or biological characteristics of water are altered in a way that causes harm to humans or aquatic life, basically making it unusable. Now think about the fundamental chemistry here. Why does this happen so easily? Because water is nature's absolute ultimate solvent. It's incredibly efficient at dissolving things. That's exactly why it's so vital for delivering nutrients to ourselves. But it's also a double-edged sword. It makes water incredibly vulnerable to contamination from surface runoff, chemical spills, or untreated pipe discharges.
Moving on to Section 2. 4 types of pollution.
Let's break down the mechanics of this crisis, starting with the most direct threat to human health, infectious agents. We are talking about biological pathogens here, guys. Bacteria, viruses, and parasitic worms originating from human and animal waste. These are the culprits behind devastating diseases like typhoid, cholera, and dysentery. And they spread primarily because of inadequate sanitation and poor sewage treatment. It's essentially taking a life-giving resource and turning it into a highly dangerous vector for disease. Just terrible.
Next up is a concept known as eutrophication, or basically water suffocation. Here's how it works. When oxygen-demanding organic wastes, like the stuff pumped out from paper mills or food processing plants, enter a body of water, they act like a massive buffet for aerobic bacteria. These bacteria multiply like crazy and literally suck all the dissolved oxygen right out of the water. In engineering terms, this causes a highly elevated chemical oxygen demand, or COD. When that oxygen drops too low, it creates literal dead zones. We're talking about areas where fish and aquatic life simply cannot survive. Suffocate.
Our third category involves silent, invisible poisons, inorganic chemicals. These are persistent heavy metals like lead and arsenic, along with toxic salts, usually coming from industrial discharges and mining operations. And the scary part, they don't just wash away. They can cause genetic mutations, and they aggressively accumulate all the way up the food chain. To put that into perspective, just look at the industrial area of Nagda in Madhya Pradesh. Severe effluent discharges there have contaminated the local groundwater with so many salts and metals that it is now completely unfit for even basic agricultural irrigation.
Now, as engineers, this fourth category is absolutely fascinating. Thermal pollution. It's actually not about what is physically in the water, but rather the temperature of the water itself. When massive power plants use river water for cooling, they discharge it back at much, much higher temperatures. This creates what we call a thermal plume. This heated water starves the ecosystem of oxygen and can trigger fatal thermal shock in aquatic organisms. In fact, a study on the Ganga River found that a single thermal discharge from a coal-fired power plant reduced chlorophyll content, which is a huge indicator of phytoplankton health, by over 34% right near the discharge point. It's a real game changer for the ecosystem.
All right, Section 3, Sources of Contamination.
So where is all this coming from? We can map out these pollutants to 4 distinct footprints. First, there's the engineer's footprint, where massive construction and impervious surfaces create tons of sediment and runoff.
Then we have industries. These act as point sources, meaning you can literally point your finger directly at a specific pipe discharging heavy metals or a thermal plume. In sharp contrast, agriculture is the largest non-point source. We're talking millions of acres where fertilizers and pesticides just broadly leach into our groundwater. And of course, our dense urban areas are pumping out massive amounts of raw sewage, oils, and even residual pharmaceuticals from our daily lives.
Which brings us to Section 4, the engineering solutions.
Now, we have outlined an undeniably grim reality so far, but let's shift our mindset, because engineers are, above all, problem solvers. I really want you to internalize this powerful statement from the source lecture by Dr. Arun. He says, "This is the reality you are inheriting, but it is also the opportunity you have. As a civil engineer, you will be the guardian of the water cycle." I mean, how incredibly empowering is that? Instead of being paralyzed by this environmental crisis, you have to recognize your immense opportunity here. Every single infrastructure project you touch is a tangible chance to protect our remaining freshwater.
And this philosophy? It translates into incredibly concrete applications. As an engineer, you have the power to design modern wastewater treatment plants that actually capture emerging threats, like microplastics and pharmaceuticals. You can engineer stormwater management systems using permeable pavements and rain gardens. You can build green infrastructure that works seamlessly with natural wetlands, rather than just paving right over them. And by implementing precision agriculture and advanced industrial effluent treatment, we can stop both non-point and point source pollution before it ever even reaches a vulnerable ecosystem.
Finally, Section 5, a call to action.
Let's wrap up today's masterclass by consolidating exactly what we've learned. We've seen how our daily societal footprint drives 4 specific types of contamination: biological, oxygen-demanding, chemical, and thermal. But much more importantly, we've firmly established that the engineering and design choices we make are the absolute frontline defense for protecting our remaining fresh water. As engineers, we aren't just pouring concrete and building structures. We are designing restorative, literal life-saving systems for the entire planet.
So I'm going to leave you with a quick homework assignment today, inspired straight from our source material. Take a walk and go observe a local river, a pond, or, hey, even just a simple drainage ditch. Really look at it critically. What does its current condition tell you about the engineering choices that led to its current state? And more importantly, as a future guardian of the water cycle, ask yourself how you will engineer its future restoration. Thank you so much for joining me for this explainer, and remember, never stop questioning the world around you.